Welcome back to Introduction to Statistics. Today we're going to talk about the language of hypothesis testing, which is another form of inferential statistics. What is a hypothesis? It's a statement about a characteristic of a population or populations. So then what is hypothesis testing, or what is a hypothesis test? That is a procedure based upon sample evidence and probability used to test a statement about a characteristic of a population or populations. Let's talk about the steps of hypothesis testing. The first step is to make a statement about the nature of the population, or more formally, form a hypothesis about a characteristic of the population. Next, collect evidence, sample data, to test the statement, and then analyze the data to determine the plausibility of the hypothesis. Is it reasonable? Is it probable? I think we need an example. So let's say I split your class into groups. These groups will not only give you practice presenting in an online environment, because that's what you'll be doing, presenting a lesson to your groups in our Collaborate session, but they will also remind you about how random processes work, because I'm going to assign one of your group members to randomly choose who is going to present, and we'll do this once a week. How's that? I think we'll go with small groups, and we'll do 4 groups. Here you are, all lined up randomly. Now I'm going to choose somebody. Okay, Michael. You're going to be the one deciding randomly, using your calculator or mini-tab, whichever you prefer, which group will be presenting each week. The rest of you trust Michael, right? Of course you do, because your hypothesis is that there is no cheating. No one in our class would cheat. So let's say that we have been doing this since the beginning of the semester, and the first week Michael chose group 1. And the second week he chose group 3. The next week he chose group 1 again. And then the next week it was group 4. He chose group 4 again, group 3, group 1. Kind of odd that group 2's not showing up here. So let's think about this. Some of you might begin to suspect that Michael might be cheating. So what would the probability be that group 2 was not chosen the first week? Okay, there are 3 other possibilities. So the probability of not 2, kind of strange way to write it, is 3/4. So, hey, no problem. Probably not going to happen that group 2 would be chosen the first week. And that probability is equal to 0.75. So what would the probability of not group 2 occurring for 3 weeks? Well, that would be 3/4 times 3/4 times 3/4, or 27/64. That's a smaller number. The probability of that is still just 0.42. Less probable than its complement, but still not too bad. You might still give him the benefit of the doubt. However, if this were to go on for, say, 12 weeks, there's only a 3.2% chance of that happening. So, by that time, you'd probably be thinking, I don't know that I trust Michael to do this. And Victoria and Robert, you might either be mad at him or you might be paying him to do this, depending on how you feel about presenting. So for the first few weeks, your hypothesis that Michael is not cheating would probably hold up. But by the time you get moving on into the semester and presentation still is not happening for group 2, your hypothesis is going to be looking kind of shaky, like you do not have evidence to support it. In fact, your evidence may be leading you to think the opposite. By the way, I happen to know that there is no cheating going on. Michael would never do that, because Michael is a fictional character. Notice that our original hypothesis was no cheating, no change, not going to expect someone to break, academic integrity. So no cheating is no change. That is known as a null hypothesis. In fact, the null hypothesis for this thought experiment. Null meaning none. No change. And that is what we test. We are always testing the null hypothesis. We always assume the null hypothesis is true until evidence suggests something different. Rather than write all that out, we just write H naught, or H sub 0. So H naught. The alternative hypothesis. This is a statement of change. Something has changed, and we're trying to find some evidence to support this. We call it H1 or H sub 1. In our case, H naught was no one was cheating, including Michael. Michael was not cheating. The alternative hypothesis was someone was cheating, and since Michael's in charge, looks like it's him. But, maybe Victoria was threatening him or something. Let's look at some more examples of null and alternative hypotheses. So, a consumer protection agency thinks that a pickle manufacturer is underfilling its 32-ounce jars. What are the null and the alternative hypotheses? The null hypothesis is what we would expect. The pickle jars contain 32 ounces of pickles and brine, just as they should. The alternative hypothesis is that the pickle jars contain less than 32 ounces of pickles and brine. Another example. The pressure in a pipe pumping chlorine gas is supposed to be held at 45 pounds per square inch. A safety inspector suspects that the pressure in the pipe is higher. What are the null and the alternative hypotheses? Pause the video. Did you get it right? H naught, the pressure in the pipe is 45 psi. H1 is the pressure in the pipe is greater than 45 psi. In 2000, a national polling center found that in the United States, the average charitable donation for individuals with income of $1 million or more was $15,000. A researcher at the polling center suspects that the average charitable donation for that demographic has changed. At this point, the researcher isn't sure whether it would have increased or decreased due to all the economic and political things that have occurred since 2000. By average, we will assume they meant mean, and therefore the null hypothesis, H naught, is the mean charitable donation among people with an income of $1 million or more is $15,000. Still, has not changed. The alternative hypothesis, H1, is the mean charitable donation for individuals with an income of $1 million or more in the U.S. is not $15,000. These three examples represent the three types of hypothesis tests. We call these tests by their tails. The first example is a null hypothesis says that the parameter, in other words, the volume of the pickle jars, that would be the mean volume of the pickle jars, equals 32 ounces. It equals a set value. That is the null hypothesis. If nothing has changed, that's how much pickles and brine will be in each jar. The alternative hypothesis says the parameter, mean volume, is less than some value, 32 ounces. So on a normal curve, we'll be looking at some value and the area to the left. Values less than the given value. So this is a left-tailed test. In much the same way, the second example gives you a parameter and asks you, through the alternative hypothesis, if the pressure in the pipe could be greater than 45 psi. Thus we have an H naught where the parameter equals some value. We have an H1 where the parameter is greater than some value, and we have a right-tailed test because we are interested in the right tail of the normal distribution. And finally we have the case where we have h0, a parameter equals some value, and h1, where a parameter does not equal that value. We don't care what else it equals, but it doesn't equal that value. And thus, we have a two-tailed test. Now, when we're working with statistics, you've already noticed that when we express a confidence interval, we do not express an exact number. We're working with a range of numbers, a lower bound and an upper bound. And this type of test is looking for what happens if the value is not within those bounds. So left tail and right tail are both part of what we're looking for. We don't know necessarily what the mean charitable donation is. We just know it is not within a range close to $15,000. Please notice that your less than or your greater than sign indicates the direction by which we name it. So if it's a less than, it's pointing left, it's a left-tailed test. If it's pointing right, it's a right-tailed test. Time for new examples. Here they are. If you look at the first example, it's talking about the mean test score. If you look at the second example, it's talking about a proportion of children. If you look at the third example, it's talking about the standard deviation, not the actual scores, but the standard deviation. That is why, in the previous examples, we always had our H null, or our H naught, written as a parameter equals some value. Remember also that H naught is always the parameter equals something. It's a statement of no change. And then we use the same parameter and either looked at it being less than some value for a left-tailed test, more than some value for a right-tailed test, or just not equal to that value for a two-tailed test. We can perform a hypothesis test for any parameter that we choose. We will start with performing hypothesis tests of the mean. For now, let's classify these examples by their tails. The mean test score for SAT Math is 516. So therefore, our null hypothesis is that the population mean equals 516. Our alternative hypothesis is that our population mean is greater than 516. Thus, we have a right-tailed test. For the second example, we are looking at a null hypothesis, or an H naught, where the proportion is equal to 0.196. I've converted the percentage to a decimal because it's often easier to use in calculations. And H1, our alternative hypothesis, is that the proportion is less than that same value. Therefore, we have a left-tailed test. And finally, we are looking at the case where our null hypothesis, H naught, is that the standard deviation of these test scores equals 112, and the alternative hypothesis, H1, does not equal 112. We don't know in which direction it is not, but it is either way. It is a two-tailed test. Now things get interesting. One of the basic tenets of our legal system is that everyone is innocent until they are proven guilty. Remember that. It will help you understand what we're going to do next. Here are our null and alternative hypotheses. However, look closely. The null hypothesis is not that the defendant is innocent. You can never prove a person is innocent. You can only say that there is insufficient evidence to show that the defendant is guilty. When a jury's verdict is announced, they either declare the defendant not guilty or guilty. And maybe they're right, but maybe they're wrong. They could make an error. When we're doing hypothesis testing, we can make errors, and there are specific types of errors that could be made. So I'm going to make this kind of small, but I'm going to leave it on the screen because I want you to remember that as we work through these concepts. So now we have to grapple with reality and with the fact that we don't know everything. So in reality, the null hypothesis may be true. Maybe the defendant is not guilty. Or, in reality, the defendant is guilty. But as a juror, you do not know. You are presented with evidence, and you must make a decision based upon that evidence, but you could be wrong. There are two ways you can be right. If the null hypothesis is true in reality, and you do not reject it, then you are correct. The way to be correct is if in reality the alternative hypothesis is true, and you reject the null hypothesis, then you will have made a correct decision. If in reality the null hypothesis is true, remember this is not something we can know for sure, but if it is true and we reject the null hypothesis, we have made an error, and we have made a type 1 error. If you are talking about you, yourself, being guilty or innocent of a capital crime like murder, and you are sitting before a jury, if you are innocent, and only you know it, and your lawyer are trying to prove you're not guilty, but the jury reject the null hypothesis and say you're going to jail or you're going to face capital punishment, that's a serious error. That is a type 1 error, the biggest error, in my opinion, that could be made. So try to remember that when you're thinking about how you type these errors, okay? The other way you could be wrong is you could have a type 2 error. That is when the defendant is as guilty as the day is long. The alternate hypothesis of guilt is true, but the jury does not reject the null hypothesis. They declare the guilty defendant not guilty. That's an error. But because we are so opposed to accidentally putting a person to death when they did not commit the crime of which they're accused, we skew our justice system so that we are more likely to let a type 2 error occur, that we are more likely to let someone who is guilty off because we do not want to convict the innocent. At least that's the way our justice system is set up to work. Another way you can categorize mistakes that are made when we're doing hypothesis testing or when you're sitting on a jury is you can consider a type 2 error a miss. Yeah, the other alternative was true, but you missed it. Or you could have a false alarm. All right, let's look at a different situation with this. Let's consider a null hypothesis of, I have a smoke detector, and my null hypothesis is that there is no fire. My alternative hypothesis is there's a fire. Okay, that alarm goes off, there's smoke, there's fire, I need to get out of there. So if the alternate hypothesis is true, but my fire alarm doesn't go off, it does not reject the null hypothesis that there is no fire, that is a miss. And in this case, a type 2 error, it can be deadly. Okay, on the other hand, if there is no fire, if the null hypothesis is true, and my smoke detector rejects the null hypothesis and says, oh no, there is a fire, I have a false alarm. A type 1 is a false alarm. Now in this case, which would you rather have? A smoke detector that is so heavily weighted against having false alarms that it misses real fires? No, we want to weight it the other way. We'd rather have some false alarms, but really be warned when our life is in danger from fire. So in this case, we tend to skew the way we set up our smoke detectors the opposite way from which we set up our justice system. Likewise, when you are setting up your hypothesis test, you will have to decide which is more serious, a type 1 error or a type 2 error for what you have designed. Now, you've already had some experience with uncertainty in this course. We have talked about how you cannot say, oh yes, based on my sample, I know the mean of the population is 356. You can say, I am 90% confident that the mean of the population is and you give a range of values. There is uncertainty in statistics just like there is in life. So let's review some Greek letters. The probability of making a type 1 error is going to be represented by the symbol alpha. Okay, and we are actually going to choose that probability before we start. We're going to decide how important it is not to make a type 1 error. Also, the probability of making a type 2 error is represented by, you guessed it, beta. For so many applications, it is important to try to avoid a type 1 error. That's what we look at when we're setting up our hypothesis test. In fact, we have a name for this alpha. It is called the level of significance. Remember, alpha is the probability of that error occurring. So if making a type 1 error, convicting somebody who's actually innocent, is so bad, you want a very small level of significance, say something around 0.01, like only 1% of the time an error occurs. On the other hand, since I don't mind an occasional false alarm, makes me know that at least the thing will alarm at some point, the fire alarm, I might go with a 5% probability, or maybe even a 10% probability. Say, let's take a weather report. If it's normally sunny and warm in August, and the weatherman gives a false alarm that there's going to be a cold front come through and it's going to be 50 degrees and rainy, and he's wrong, I'm pretty happy about that. I can deal with that. But if it's a big thunderstorm with devastating winds and a tornado and he does not forecast it, then I have a problem with the forecast. Okay, I know this is a long video, but we need to cover one more thing, and that is how you express conclusions when you're dealing with hypothesis tests. We will not get into the nitty-gritty today of calculating what you need to calculate, but you need to know how to express your conclusions. So here's one of our examples, and here are the corresponding null and alternative hypotheses. Now, your mission, should you choose to accept it, is to express how you would reject the null hypothesis. How would you tell someone you're rejecting the null hypothesis? I will show you how to do this so that you're not just saying, I think that's right. You will have sufficient evidence to conclude that the pickle jars contain less than 32 ounces of pickles and brine. That is how you reject the null hypothesis. Oh, but if you do that, and you are wrong, if you made an error, what type of error have you made? You have made a type 1 error. It is a false alarm. It's not true, in reality, that the pickle jars contain less than 32 ounces of pickles and brine. But you don't know that, and your evidence suggests differently. When you're expressing this, that's why you say there is sufficient evidence to conclude. You're not saying absolutely there's less than 32 ounces of pickles in these jars, but there is sufficient evidence to conclude that the pickle jars contain less than blah. Never accept the null hypothesis. You never know what's in someone's heart. You can never say they are innocent. You can never know, more importantly and precisely with statistics, you can never know exactly what the population parameter is because you have not sampled the entire population. If you did, you don't need to worry about inferential statistics. You have everything you need to know. But if you are trying to perform inferential statistics, you will never be able to know exactly what that parameter is. But let's say instead you want to reject the alternative hypothesis. Instead of rejecting the null hypothesis, we're going to reject the alternative hypothesis. How would you say that? Well, you could say, based upon your evidence, there is not sufficient evidence to conclude that the pickle jars contain less than 32 ounces of pickles and brine. You could say there is insufficient, but sometimes people mishear that. You could say there is not enough evidence, but usually I will choose to say there is not sufficient evidence to highlight that it is the opposite, the other possible conclusion. And what type of error may you have made? You may have made a type 2 error. You don't know for sure, but you may have made that. There's a possibility that you miss the evidence that that manufacturer is underfilling the jars. One more, and we'll call it quits. Here's the example. The pressure in a pipe pumping chlorine gas is supposed to be held at 45 psi. Remember this one? The safety inspector suspects the pressure in the pipe is higher. The null and the alternative hypotheses. In this case, I would like for you to reject the alternative hypothesis. So reject H1. Remember, we always assume H naught is true. The null hypothesis is true. So it's going to take a lot of evidence to suggest otherwise. If you're going to reject the alternative hypothesis, then you'll do it because you do not have sufficient evidence to accept it. Therefore, when choosing here, you would say there is not sufficient evidence to conclude that, and then you throw in your details. There is not sufficient evidence to conclude that the pressure in the pipe is greater than 45 psi. So your details come from your hypotheses. I would like for you to reject H naught. Notice that effectively means you are accepting the alternative hypothesis, and you can do that. You can say there is sufficient evidence to accept it, but it's easy to get confused that way. Better to look at it as either there is or is not sufficient evidence to conclude that whatever. So in this case, if you are rejecting the null hypothesis, then there is sufficient evidence to make you do that. Okay? So there is sufficient evidence to conclude that, go back and get your details, there is sufficient evidence to conclude that the pressure in the pipe is greater than 45 psi. All right, that is a lot of new vocabulary and a lot of new concepts. So please join me and collaborate so we can discuss this further. See you there.